Today we'll derive the heat diffusion equation in 2 dimension. So as conduction heat transfer, conduction heat transfer, and in conduction heat transfer we'll derive the heat diffusion equation in 2D. All right. So to derive this equation in Cartesian coordinate, what we'll do is we'll consider a differential element. A differential element is a rectangular shape. So it is like this, where this is your dy, this distance, and this is your dx. And from left to right, heat transfer is happening. So on the left wall of this differential element, it is Qx, and is going out from here, which is Qx plus dx. Similarly, from the bottom, it is Qy, and from top is going through the top surface, which is Qy plus dy. Alright, so these 4 sides finished, and the inside we have some heat generation, and we also have the heat storage. Alright, so that's all. And now what is Qx? Qx is the heat transfer. Alright, so this is defined by Qx is equal to, you know that I already showed you in lecture 1, minus Ka so minus Ka del T del X. Alright, so now what is the area? So Qx is acting here, the left wall. So what is the area on this surface? What is this area? Because it's a 2 dimension, so there is no z. So along, like the perpendicular on that is your z direction. So no z means we can consider this 1, and actually no only the y. So it's start from here, only the y is there, x is there, so there is no x. We consider x as equal to 1. So that means it will be minus k dy. So that is the area. The area means the length for this case, okay? Because it's a is actually not 2 dimensions, just one side is 1 dimension. So dy times del T del y. So this is your Qx. Now the right side, Qx plus dx. So this Qx plus dx, we can expand it using Taylor series expansion, which is, I believe you know it, which is Qx plus del x of Qx times dx plus higher order term. We are not going to consider that. Alright. Now Qy, similar way to the Qy. So minus K A del T del y. So here in the bottom. Okay, so which is equal to minus k. What is a here? What is your a? For this surface, your k is, so this surface, the k is your the area is only dx. All right, there is no dy and there is no dz, only dx. Okay, so that dx del t del y. Now what left? Okay, the q y plus dy. Again, we have to expand it using Taylor series expansion, which is qy plus del del y of qy into dy plus higher order term. So we have 4 terms here. Now what else you need to find out is heat generation. So that is your E dot G. How to define heat generation mathematically? So the heat generation actually Q dot the volume. Okay, Q dot volume. What is Q dot? Q dot is the volumetric heat load. Okay, so that means in the whole volume how much heat is going to transfer. So that is your Q dot. And what is the volume? Because it is a 2 dimension, so we have only x and we have only y, we don't have z. So z direction we consider as 1. So it should be dx dy. Now just one note, which is, we can just mark it this one. We already explained in your lecture 1 that Q, we define Q as, how did you define? The unit of Q is what? And unit of Q double dash is watt per meter, and Q double dash is watt per meter square, which is actually the heat flux. And this is the heat transfer, heat flux, and it does not have any name. Now we got another one here, so that is Q dot, which is actually watt per meter cube. So that consider the volume. So now we have one more thing is the heat generation. Storage. Heat generation. How do we define the heat generation? So the heat generation is, sorry, not heat generation, heat storage. Heat storage is mass into Cp times dt del T del T. Okay, so this is the definition of heat storage. So now what is mass? So mass is rho times the volume. Okay, rho times volume times the Cp is here, Cp del T del T. Okay, which is equal to what is the volume? You know, dx dy. So rho Cp dx dy into del T del T. So we defined all here. Now we have to consider the energy balance equation. What is your energy balance equation? So the energy balance equation is your energy in minus energy out plus heat generation is equal to our energy generation equal to our energy storage. Okay, so that is our energy balance equation. We talk about this one in our lecture 1. So now we know this here. Now energy in means, so energy in is this one and that one. So these two energy in, and energy out is this one and that one is energy out. Okay, so now energy in is your Qx. So Qx plus Qy. So Qx plus Qy. Now minus energy out. Energy out is the blue, this one and that one. So we did the expansion. So it will be like Qx plus del x of Qx dx plus another term Qy. Just a sec, I give a line here. Okay, so and Qy plus del y plus y of Qy dy. Qy dy. So and then plus energy generation. So energy generation is Q dx dy is equal to energy storage. So rho Cp dx dy del T del T. So if you see very carefully, you can see the minus. So minus Qx plus Qx cancel. So this minus, so here is a minus. So this minus this is cancel. So the leftover is minus this, right? Minus del x of Qx so Qx we need to you can just expand it here then. So Qx, what is Qx? So Qx is your minus k dy and dt del t del y. So that is your times dx. So this one is finished. Now minus. So this term del t del y of what is qy? Qy is minus k dx del t del y and dy. Okay, and the leftover is here plus q dx dy is equal to rho Cp dx dy del t del t. Now again you can see the both side what is common. So dx dy we can cancel it or divide by something. Okay, so this page is over. Now what should I do? Okay, now which gives us del x of k. So minus and minus plus, so we had a minus here, so del t del x plus del y of k del t del y plus q dot is equal to rho Cp del t del t. Okay, so now divide by, so now divide it by k. Okay, so if we divide it by k, then what will happen? So we have k in term 1 and term 2, this term and this term, and we don't have k over there. So when we can actually divide k, if k is a constant, so that means the constant property, if we consider the constant property of a material, then we can divide it. But thermal conductivity sometimes depends on some maybe temperature or something. So, but for this case, we are considering thermal conductivity is constant for this this material we use. Okay, so then it's a constant, so you can take it out from the differentiation. So k, if we divide the k, it will be del square t del x square plus del square t del y square plus q dot by k is equal to rho Cp by k del t del t. Now, what is rho Cp by k? So this rho Cp by k is 1 by alpha. Okay, so the thermal diffusivity. So that means is equal to 1 by alpha del t del t. We can write the complete equation. Del square t del square t del x square. So that is your heat diffusion equation. Okay, so this is our heat diffusion equation. So now to solve this problem, this is a differential equation, second order differential equation. To solve this equation, because it is general solution, so if you have some specified geometry or something, you need to have some condition. So this equation can be solved under certain condition. So there are two types of condition we'll use here. One is called the initial condition and another one is called the boundary condition. So the initial condition means what is the initial status, like how it was, what is the temperature like when it just started or something like that. And the boundary condition we want to use for like the material we are considering, not a material like the heat conduction we are calculating through something, So if you know their dimension, if you know their surfaces, from which surface to what surface it is transferring, then we have to consider, we have to define the thermal condition or some other conditions on the wall, okay, from which wall to the other wall. So we need to define that one. So that is called the boundary condition. So we will use about maybe only for our cases, we will consider only 4 boundary conditions and one initial condition. So the initial condition is so at T is equal to 0, when we just start, we assume the temperature is something like Ti, for example 290 or 300 Kelvin. Okay, so that is our initial condition. Okay, for example, we want to measure the wall of this classroom. The wall, we know what is the initial condition. We can use the thermometer or something, and then we can measure what is the initial condition, what is the initial temperature here. So that we can do. Now the boundary condition. So the boundary condition we will write down like BC1, boundary condition 1. So the first condition we can use is called the constant temperature, surface temperature. The constant surface temperature means like this is a wall. The wall condition is like this is wall, and we know the thermal conductivity because we have to know the thermal conductivity. So K is here, and if we consider the x-axis like this, okay, so this is the wall, x-axis is here, and this is actually x equal to 0, the wall is, okay. So now T temperature on this surface, x equal to 0 means on this surface, is equal to our Ts constant. Okay, so that means our boundary condition 1 is T x equal to 0, and for any time, because this constant always at any time, T is equal to any value, is our Ts. So this is our constant temperature condition. Now we will consider the second boundary condition can be boundary condition 2 is consider the surface, thermal conductivity is applied, and this is your x-axis, and this is your x equal to 0, and here we will consider constant surface heat flux. You know the heat flux, right? So that means the Q double dash on the surface is constant. Okay, that the change of the rate of change of temperature on this surface is constant. Okay, so how can we write that? So we know that the Q equals Q double dash equals minus K, no area because it is Q double dash, so no area here. So that is del T del X at x equal to 0 on the wall. This should be your surface heat flux. You can, it is, yes. Now BC number 3, boundary condition number 3, that can be perfectly insulated. That means adiabatic. Okay, so how is that? That is your heat flux on the surface is equal to 0. So that means minus K del T del X at x equal to 0, 0. So that is the boundary condition 3. The adiabatic insulated or perfectly insulated. Okay. Now BC number 4. BC number 4 is called convection on the surface. Convection on the surface. So you know that the wind, for example, plays an important role for heat transfer. So if there are some winds outside, then the heat transfer through the wall, I mean on the surface, outer surface, is due to convection, because the wind the air can take away some heat. Okay, so that means we have to consider that one. So what happened is there. So if we have like some surface is this, so thermal conductivity, this is our x-axis, and we have some wind. Okay, so that wind is here and the temperature is T infinity, and then we have the heat transfer coefficient is our H. It should be defined, or we have to calculate it. And then because the heat convection is happening outer surface here, and then the heat is going into the surface, and that heat, because it is a solid, is the conduction happen after that. So it is a combination of conduction and convection. So that means the conduction, the heat conducted through this wall minus K heat flux del T del X at x equal to 0 is equal to the heat convection. So is T infinity minus T x equal to 0, the wall. Okay, ambient temperature and the wall. So this is your 3 boundary condition: boundary condition 1, boundary condition 2, boundary condition 3, boundary condition 4. So boundary condition 1 was constant temperature, boundary condition 2 was constant heat flux, all right. Now in chapter 3 we'll deal with like a one-dimensional problem. So if the problem is one-dimensional, what will happen? So if the problem is one-dimensional, what will happen? So 1D, you can consider 1D, one-dimensional and steady state. And we consider T1 is greater than T2. So for example, we see two surfaces of a wall. Okay. So this surface we consider T1, this surface we consider T2, and the heat is going like as a heat flux is the amount of heat is going here, the same amount of heat is going away. And then we can also consider the x-axis and the length of this wall. We consider L. What else? That's it. Okay, so now what is our heat diffusion equation? So the heat diffusion equation is del square T by del x square plus del square T del y square. So the one I uploaded in the UTS online, I just checked that del x square is missing, so it should be del x square anyway, and then plus q dot by k is equal to 1 by alpha del t del t. Now it is on dimension. So on dimension means there is no dy. Now steady state, so that means it's not time dependent, and also you can consider no heat generation, so this one is cancelled. So under this assumption, our equation now becomes very simple. Del square T by del x square is equal to 0. So just keep in mind, this is a general equation. Now we reduce to very small equation, but we assume something. So that's the reason if you solve any problem in your final exam or maybe in the quiz, so you have to write down all the assumption you have made. Okay, so this here, what are the assumptions? So number one, it was like a no heat generation, no heat generation. Number two, steady state. Number three, only, what else? Steady state only, no heat generation. That's it. So these are the three main assumptions we made. Okay. So now how to solve this problem? So because it is now on dimension, so we don't need to give the partial one. I can write d square t and d x square is equal to 0. Now we have to solve this equation. So it is very easy to solve. Just do the integration. So if we if we integrate at first, what will happen? dt dx is equal to some constant c1, because you know that when you do an integration, always there should be some integration constant. Okay. Now if we integrate again, so it should be t is equal to c is a constant, so it should be x plus c2. So we have two constant here, so you can call it is a function of x only. Okay. Now we have to apply boundary condition. So what is the boundary condition? You see the left side is T1, right side is T2, is a constant temperature. So the boundary condition 1 is at x equal to 0. So this is x. So x equal to 0 here, x equal to L here. So at x equal to 0, it is T is equal to T1. Okay. So x equal to 0 equal to T equal T1. Now BC2 at x equal to L, T is equal to T2. So we have two boundary conditions. So now if we put this two boundary condition in here, then we can easily get the solution. So this is a general solution. Now you can get the specific solution. So at x equal to 0, so that means T0 is equal to T1, which is x equal to 0, so this term is 0, so C2. So C2 equals to T1. Now again, x equal to L, So T x equal to L, which is our T2, is equal to C1 L plus C2. So we know that T2 equals C1 equal to T1, right? T1 L plus C2. So C2 equals T1 L C2 equals sorry should be C1 L and C2 equal to L. C1 L plus C2. Okay, so put C2 here, and then C1 should be C1 here. C1 plus T1. So the C1 equal to T2 minus T1 divided by L. So our specific solution Tx equals, so we know C1 T2 minus T1 by L times X plus T1. So you can see here some interesting. So this is our slope, right? This is our slope, and you can see the T1 is greater than T2. T1 is greater than T2 means it is negative. Yes, you're right. So it is negative. If it is negative, the slope is negative. So it's going from here, and also is a y is equal to mx plus c is a linear equation. Okay, so that means a line. So from here to there, so it's a linear line and slope is negative. Okay, so this is our solution for one-dimensional here. So now we got the temperature solution. Now we have to calculate the heat transfer. So what is heat transfer? So how to calculate the heat transfer? So Q is equal to minus K A del T del X. Okay, so minus K A, so del T del X. So del T del X you have to differentiate. So your Tx was T2 minus T1 divided by Lx plus T2, right? Now if you want to differentiate it, so del T by del X should be T2 minus T1 by L. So it should be T2 minus T1 by L. So which is, if we just exchange like a T1 minus T2, then the negative will be gone. So T1 minus T2 divided by L divided by Ka. Can we think about this one? Okay. So this is our Q. So Q is this. So easy to get it because we know the area, we know the thermal conductivity, we know the length of the wall, and also we know the temperature. So it is easy to calculate the Q. Now just observe I equals del V by R. So this is what? This is Ohm's law. So what is Ohm's law here? The electric current equal to the difference of the voltage divided by the resistance. If you compare these two, you can get similarity. So these and these has a similarity. So due to voltage difference, electricity happened, and here due to temperature difference, heat transfer happened. And the denominator R and the denominator L by Ka, it's called the thermal resistance. Okay, so delta T divided by thermal resistance. For electricity, voltage difference divided by resistance. So this is L by Ka is your thermal resistance. So if we have like the wall is not like a same material, if we have different material, and if you know the thermal conductivity, different thermal conductivity, and how much it is, like the area, then we can get some circuit, and using that circuit we can solve the heat transfer. So that circuit can be parallel, can be series. All right. So for this case, so for example, here we have T1, and from T1 we have some thermal resistance, and then we have T2. So this is we call L by Ka. So this is thermal resistance. All right. Now this is for the conduction. If it is for the convection, Ts, surface temperature, and if we have airflow with T infinity, so we know the our surface, our heat transfer is Q is equal to H A Ts minus T infinity for convection. So heat transfer coefficient, your H, and the surface area. So this is the area heat is convecting away. So that is your surface area times the surface temperature minus the ambient temperature. All right. So here you can do the similar things. Ts minus T infinity divided by 1 over HA. So this is the resistance. So this is called the convection resistance. Okay, this is called the convection resistance. So we can also do like this way. Here we have temperature Ts, here we have temperature T infinity, and here 1 by HA. So the convection resistance. Now this one. Okay. Now the composite wall. If we have composite wall, composite wall. So we assume that this is the wall, composite wall, and we have thermal conductivity Ka for this. This is Kb, and the length from here to there is La, and from here to there is Lb. So here the area, this surface area is AA, here the surface area is AB, and what else? Okay, and this is your T1, this is your T2. So T1 is greater than T2, assume that, and also we assume that Ka is greater than Kb. thermal conductivity. So 2 thermal conductivity. So the left side portion, the conductivity is higher than the right portion. So now draw the thermal circuit. Okay, so draw the thermal circuit. So draw thermal circuit. So it's from Q1. So Q start from here with the temperature T1, and then resistance, then another in the middle, then resistance, then T2, and the flow. So the thermal flow is this. So now this resistance is the left side, right? So LA divided by KA AA. This one is LB divided by KB AB. Alright. So the Q is, so temperature difference T1 minus T2. Because it is series, just add this to resistance. So LA divided by KA AA and plus LB divided by KB AB. But actually two surface areas are the same, AA and AB, they are the same. So if they are the same, then what we can do is we can take on the left side, which is Q divided by A. Actually this is our heat flux, which is T1 minus T2 divided by LA by KA plus LB by KB. Alright, so that means we know all of this, so it is easy to calculate the heat flux. Now if we add something else, if we add like the convection, so that means T infinity 1 on the left, so air is flowing from the right, T infinity 2, T infinity 1, T infinity 2, and then we have another thing is H. So H1 is here, H2 is here, and what else? Yeah, that's it, extra things. Now so on the left side from here to there, convection, conduction, conduction, and then convection again. So if we start from here, T infinity 1 and then resistance, so then now T1, okay, now resistance, so now in the middle, now resistance, now here T2, now here resistance, here T infinity 2. Okay, so that means here 1 by H1 AA, 1 by LA by KA AA, LB by KB AB, and is 1 by H2 AB. Okay, so the similar way we can get the heat flux. We can take this one is your T infinity 1 minus T infinity 2 divided by 1 by H1 plus LA by KA plus LB by KB plus 1 by H2. All right, so this one is done. What else we can do? We have another one, another one is called the parallelon. I think is easy. You can do it by myself. What else we can do is we can just do for the circular cylindrical condition case. Just very quick, I'm showing the cylindrical condition. So the cylindrical condition, the cylindrical condition, so that is the cylindrical coordinate. Okay, so sorry, not condition, conduction. Conduction. So the coordination will be cylindrical. So we consider on cylinder this and this. So we have this radius, if we call it R2, and if we call this on R1, then R2 is greater than R1. The similar way, we have to take a differential element. Take the differential element like this. Sorry, differential element is this. Okay. So this one, this difference is, we call it dr. Okay, so if we make it like if we take this differential element, so this is your differential element. If we take the differential element out from there, it will be like okay. So from here, sorry, this is the center. Here is R, any radius. All right. So this is outside, this is inside. So the QR, and outside it is sorry, other direction. Now the direction, this direction, QR plus dr, because this is from here to there is dr. Okay. So the energy balance, we are not considering other things, we are just considering only energy in and energy out. So the energy balance equation is energy in equals energy out. Okay, so that means what is energy in? Energy in is your QR, energy out QR plus dr. Use the same the Taylor series expansion. So ddr of QR dr. Okay, so we actually make it shorter because we are not considering the heat conduction, heat generation. We are not considering the heat storage. It's just considering energy in, energy out, and it will be like a on dimension, and no it is steady state. Okay, so now you can see this one and this one cancel, and then it will be like what is QR? We know QR. So del R of minus Ka, so that is the surface area, and dt dr and dr, which is 0. All right, so that means ddr of minus K. Now what is the area? What is the area of this? 2 pi RL, right? 2 pi RL, and dt dr is equal to 0. So now If we consider the constant thermal conductivity, and also these are constant and this is constant, so you can take it away. So if we take it away, then what is left? So left is your DDR of R dt dr that is also is not 0, so that is also gone. So this is equal to zero. So now how to get it, how to solve this problem? Just integrate. Similar way, the first integration will be R dt dr is equal to some constant. Okay. Now the second integration, before you do the second integration, it is wise to take your R to right side, C1 by R. Now if we integrate again, then it will be dr equals, so 1 by R, so C is constant, so constant will be here, 1 by R is your ln R plus another constant C2. Okay, so this is your general solution. Okay, now we have to apply two boundary condition. Boundary condition number 1 is R is equal to R1, so inside T equal to T1. So another boundary condition 2, R equals R2, T equals T2. Okay, so now if we put this value here, like a two boundary condition here, so your solution will be dr equals T1 minus T2 by ln R1 by R2 ln R by R2 plus T2. So that is your complete solution. Okay, so now if we want to do like the QR, if we want to calculate the heat transfer, you have to differentiate this one with respect to R. So if you differentiate this one with respect to R, so your dt dr, and then so this is constant, and only this is your this R, so you have to differentiate this, and this is your constant, it will be on the left side. So if we just value QR, so to do that QR, so QR is minus Ka dt dr, which is minus K 2 pi R L into dt dr, the area of the cylindrical surface, which is 2 pi KL T1 minus T2 divided by ln of R2 by R1. So that is your QR. Okay, so we can reorganize this one again. So this is T1 minus T2 divided by ln R2 by R1 divided by 2 pi KL. So that is our thermal resistance. All right, so that's it. My power is going to go, so we need to save it now. Thank you very much for listening.